All right. So this is tuning Linux for performance. I want to go fast. We have sponsors who are awesome, especially this one. It's the best one. Okay. Anyway, well, that was me. I'm Anthony Nocentino. I'm a principal field solution architect at Pure Storage, which literally my job is system architecture and performance. So I literally like to make things go fast. I'm the guy that likes watching backups run to see how fast I can actually make them go. Or if you were in the last session, restores. I blog a whole bunch around topics like this, and I've written a bunch of content across various mediums like books and Pluralsight and things like that. Ideally, we have one slide today. The next slide, not this one. But we're going to talk about what there really is in a computer system that we can tune, right? There's lots of nerd knobs inside of Linux that we can get all into. But today it's more about the process and kind of the big picture items that we have to tune a system, right? And we'll talk about things like CPU, memory, and disk and file system tuning today. I'm sad about that. That slide's off right there. Yeah, his space. Yeah, hold on, let me fix that real quick. I'm gonna leave networking off the table today because I'm gonna focus on a particular type of workload. One of the more obvious things when you're working inside of a scale-up system like SQL Server or even scale-out platforms like web servers is the number of cores to do work, right? There's really not a lot that we could tune on an individual processor, right? It's going to be this fast and have this many. But there are a couple things that we can touch to make things go faster, particularly things around clock rate. I don't know if you know, but the influence that power management has on clock rates. If you're of a certain age, you know what a turbo button is on a computer, right? Remember, like I remember mine was like 8 megahertz, man, and then 12 megahertz if I hit the turbo button. Well, that changed the clock rate inside the processor. Basically, it applied more power to that system to affect that performance. We're going to look at some of the power settings that are available to us in a Linux platform and the impact that they have on a system. One of the cool things about Linux is it shows you the gory details about what's going on behind the scenes. I remember the first time I installed Linux, I was like, oh, that's what's happening when a computer boots up. And so we're going to see that today, because on Windows, we all know it's best practice to put high performance power plan. But what does that really mean? That means we're adjusting the clock rate potentially on the cores in the system. So what's that going to do? That's going to affect how fast a thing can go through a processor, right? Memory, a big one is having enough. DBAs in the party, right? Systems folks, right? Yeah, having enough memory, because we're going to talk about how diabolical swapping actually is. Who's ever had a production system swap, right? And actually had to go and deal with that. It's like the worst feeling, because there's like, oh, that server is moving out at like milliseconds, whereas before it should be operating at nanoseconds when we're talking about paging. We're also going to play with page size today. Inside a physical chip, inside of DRAM, generally going to be a 4K page. But we're going to mess with the structure inside the kernel, which is the page abstraction of the actual physical page inside of the DRAM itself. And we're going to look at the impact of that in high-performing workloads and a couple of fun stories that I've had to deal with in the customer base that I worked with when I was consulting. File system block size has a huge impact on how fast I can do a thing, or more precisely, conduct an I/O. But a bigger block size might not be great. You want to choose a block size that's appropriate for your workload, and we'll look a little bit about that. There's a concept called read ahead, both at the block level and the file system level on disks. Anybody want to take a guess what that does? Close, yeah. If I'm reading contiguous blocks or continuous segments in a file system, I'm going to read the next one too, because chances are I might need that next one if I'm scanning in the file system or at the block level. And so then when I get that data, it's already going to be in the page cache, which is an unfortunate name, for the file system, right? So yeah, they're also going to differentiate between the types of paging. There's good paging and bad paging inside of Linux. And there's also the ability to impact how we can mount a file system, which basically is the configuration parameters that we can tune to say, I want to do a particular thing when I mount that disk at this file system location. Sound fun? Everybody ready? Cool. It's all demos now. All right, cool. I did this. This is the first time I'm doing this talk. So this could be 15 minutes or 3 hours, depending on what rabbit holes we go down. Right? Oh, okay. You're going to hold me to that? Okay. Not going to be 3 hours, mate. Got it. So this is an Intel Mac, which is important for the conversation. I have an AMD Mac in there, which I love. That's a whole nother show. And I have a VMware VM running Ubuntu here with 4 vCPUs and 12 gigs of memory allocated to that VM. This is all important because if you want to go and reproduce this, this is basically how you do that. I have the max memory for SQL Server set at 8 gigs. What we're going to talk about today is a lot of SQL Server stuff, but this can apply to general computing systems. I really want to highlight what happens when you turn a nerd knob. I'm not going to tell you best practices because that's stuff that you're going to have to go figure out in your workloads, right? If you have a web server, if you have a database server, a caching server, now you know where to tune. I can't tell you exactly what to tune. That would be a whole weeks-long workshop. I also have all the code here for you to reproduce the setup exactly as I have it. And this is, like I said, Ubuntu 20. So on the left here, I have an SSH session. We're going to bounce back and forth between this here and the code I have on the right. Everybody okay with dark mode? Yeah, it's cool, right? It's a lot cool. I think on the monitors, it's working better than it does in the other rooms. Cool. Thanks for agreeing. Who's familiar with HTOP as a monitor? It's like Task Manager for Linux, but it gives me a lot of information about the system, and we're going to use this to highlight some of the things that this platform does. So let's talk about tools and techniques first. Where do I turn the nerd knobs is what we're going to talk about now. Like where are the settings that I want to work with? And the Linux kernel or any kernel for an operating system has the responsibility of controlling access to hardware. That's its job, right? Allocating the resources of who interacts with the actual devices in the box, right? So it's in charge of CPU, disk, RAM, and networking, but we left that out of scope for today. And so there's this command called systemctl or system control or sysctl, whatever one it is. I think there's probably some debate on some Reddit channel about that. So if I do sysctl -a, these are going to give me all of the different configuration parameters for the kernel that are exposed to me to go touch, right? These are the runtime values right now in the operating system, okay? And so VM has to do with virtual memory, and you have all the way up to networking. We're going to get up to file system stuff in a minute, but there's lots of things to work with. And so some of the ones that we're going to look at today, swappiness, right? And we're going to look at things like overcommit ratio. But just to show you where this stuff lives. And so if you're looking at generic documentation for tuning, so if maybe a third-party software vendor or a blog post that you read says tune swappiness down to 10, you can go do that here. Right, you can actually just change that value by typing sysctl -w and then setting the value by typing the field and the integer value. But when you reboot the system, what's going to happen? It's going to go back to the default. And so one way that you can make a change persistent is by editing this file here, etc sysctl.conf. And inside of here, when the system boots up, it's going to look in this file and it's going to find values. So a lot of these are commented out just for examples. And if we go to the bottom, I thought swappiness was in here. It is not. But we could add swappiness to this and set it to a particular value. Okay. But who likes editing config files all the time, right? They're challenging. They have to remember where the bodies are buried from a config standpoint, things like that. So one of the things that came out over the years for tuning a platform is this, ToonD. And so ToonD is a piece of software that you can install on Ubuntu. It's on Red Hat and CentOS and all those, the Red Hat variants by default. But now it's available on SUSE, Ubuntu, and so on. And so the installation of this is included in the notes at the top. And so when I work with something like ToonD, it gives me profiles to work with based on the types of workload. And so we can look at things like the default. We can look at, going down a little bit further, latency performance, which we're going to focus a lot on today. There's one for SQL Server. Going down a little bit further, we see AC power save and battery save. So a lot of things having to do with the power savings on a system. And so we'll look at each one of these individually in a moment, what they look like on the inside. But I can also ask ToonD, hey, what do you think I should be? I'm a virtual guest, which I really am in this case, right? And so it looks at the hardware configuration of the platform and makes a suggestion to you. And then I can ask, hey, which one am I actually using? I'm using virtual guest. And so rather than go and touch all those things in sysctl and have different configuration elements across the platform, it's kind of unified here to give you an interface to work with. And now we have an INI-like representation of our configuration. We can inherit config. This particular one for virtual guest is inheriting the configuration of throughput performance, okay? And there we can see VM dirty ratio for this particular profile is 30. Our sloppiness is also 30, and that's in the virtual guest config. If I go look at throughput performance, so these all live in USR lib, ToonD, then the profile name, and then toond.conf. If I run this here, I can see a whole bunch more settings. So the set of the two config files brought together because of the inheritance here is what's important. So the first thing is we're hitting the turbo button. We're asking the operating system to tell the system or the CPU to run at the highest clock rates, which is a thing called P states, and also to disable what's called C states, or the ability to turn off cores based on idleness, right? Which is really important if we're looking for high throughput systems. And so that's what we're going to look at first. Yeah, so other kernel parameters for sysctl are there. I'll talk a little bit about kernel scheduling later on. Dirty ratio, and if I go to the bottom, swappiness is now cranked down a little bit more. We're going to talk exactly what swappiness means here in a second, but just know that that value is getting incrementally smaller as we dial up our throughput requirements for I/O. Okay. Any also questions or comments throughout, please. If you're like, this is totally like garbage, let me know. It's all his fault. So that's kind of the lay of the land. We are going to work with ToonD, but we're also going to turn some NURB knobs individually and then roll those configs back into ToonD because I want them to persist on reboot, right? And I want to have a unified place to work with. And so we're going to start working with CPU now first. So I have lots of comments in here about definitions and things like that. So for example, if you want to go read exactly what C states and P states are, go check that out. But effectively, C states cuts off cores based off of the utilization, and P states is the turbo button, right? It fluctuates the processor frequency for its clock rate. So I have a whole bunch of comments in there about that. So funny thing enough, and I really wanted this to not be the case, but I can't talk to the cores on this system from the kernel, right? Because the VM, okay? So I ran this code on, well, Bob Pusateri. Hi, Bob. Ran this code for me on a physical machine. By the way, ask a friend if they have a physical Linux box. Not a lot of people reply, right? This day, nowadays. So the command to tell the operating system, or to ask the operating system about its C state configuration, is CPU powered. So now we're bringing another tool to the party, right? I have to go execute commands with CPU power to go and say, I want you in this particular C state configuration. Cool thing is, ToonD handles that for us, right? And we looked at that top part CPU, it had these settings actually affected. So I limited this to one output because Bob's computer, had 4 cores in it, or 4 sockets, but I just limited it to one output. And so we can see here, this particular system had 6 C states, poll and 1, and C6 and C7, and some variants around that. And if we look at things like latency, well, it's a microsecond for that core to respond to an instruction. If I go up a little bit higher to like C6, we can see 80, 200 as I go up higher. And so basically that higher increment number on the C state, the longer it takes for that core to come back online to reply to a request, right? Which really sounds great from a performance standpoint, right? I have to wait for my process or my thread to hit a core. It does not sound great. So what I asked Bob to do next is to investigate. So that's the C state configuration of Bob's computer. The P state configuration is this. So if I CPU power minus C, so give me the P state configuration of all of the cores. And so this particular system can fluctuate between 480 megahertz and 2.08 gigahertz. That's a massive range, right? And that's going to affect how fast things move through that system. When working in the SQL Server space, clock rate defines basically how fast I/O can be conducted, right? Because something has to read, process it, and go through the cores to access it. And so when I'm designing high performance or high throughput systems, that's a key design factor there. Now, in modern computing data centers, you might have green initiatives, so you might not want to be doing exactly this, and I'm totally okay with that. But so take that into account when you're designing the platform. But this particular point in time, when Bob asked what the clock rate was for his system, 669 megahertz was the actual reported clock rate because it was just an idle system sitting in the corner of his office. And so that's a huge range when you consider the maximum is 2 gigahertz, right? So if you're, a CIO or director and you're spending $7,000 a core for SQL Server, do you want it running at 480 megahertz, right? That's going to be not great. What's up?
How do they switch between C states and P states?
The system does that based on it's the operating system's responsibility to determine that based off of the load on the system. And the load is a metric and things like that we'll talk about in a second. Cool. Good question. So to change that, we can go ahead and, are you going to tell me to repeat the question? Because I totally didn't repeat that question. The question was, how does the system know to move between P states and C states? And that's based off of the load on the system itself. So, yeah. And so to make that high performance for the C states, this is the code here. And so you can see it changing it there. I can't run this code interactively again because my computer system is a VM. And then for the system to run at the highest clock rate, it's this code here on 187. But again, this is going to be buried inside of ToonD in that CPU section, so we don't have to go and do that by hand. So if we go here just one last peek, we'll see those values set here. Cool. All right. Any questions or comments around that, team? What's up, Joe?
Is there any reason why somebody would not completely disable C states and P states to just basically try and run everything full out all the time?
That's right. And I'm not quite getting the question.
Is there any reason why you wouldn't hit the turbo button all the time?
Oh, yeah. Is there any reason why I wouldn't want C states, or why I would want C states enabled, right? Save power, money, green. Like that's a valid data center heat, things like that. Non-production systems, right? Things like that. So, who's familiar with the concept of kernel mode and user mode? Cool. Okay. So when I ask a system to do work, it's reported back to us in oftentimes % utilization, right? And if you're looking at % utilization, I always jokingly say percentage of what? Like, it's like, how do I grasp? Like, is it a percentage of the clock rate? But what's the actual measurement that I care about, right? And we're going to talk about that in a second. But when I ask a computer system to do work, which I'm doing here, I'm doing an artificial test of CPU utilization. You see how all 4 cores now are screaming at 100%, and it's green. In that case, it's user mode CPU work, which means my task is on the core just doing work, and the program state's constantly moving forward. But if my task had to go conduct an I/O, it's going to switch off the CPU, conduct the I/O, whether it be network or file system, and that's going to be reported. That part where it goes out into the kernel to conduct that I/O is going to be reported as kernel CPU time. Okay. Now my program state's actually stopped doing that work. And then my thread will be put back onto the processor. The I/O will be brought into the context, and then I can move forward. I'm in the program state. And so if you're waiting on I/O, that's a bad thing. One of the nerd knob from a tuning standpoint I wanted to talk about is this. So task set gives me the ability to limit the cores that a system runs on. And so I can just take that same exact thing that I ran and limit that to 2 cores. There's also a concept called control groups, which will allow me to limit the amount of cores associated with the process. If I wanted to say, you know what, you can only use 20% of the entire system. And so these are ways that you can control workload. But we're focusing on how can I make the system most I don't want to say performant because that's not a word. It's not a word. The other thing that we have to affect change on a workload is this thing called niceness. Niceness effectively is a priority for a task, and a task could be a thread or a process. And so here we can see priority is reported 20 being a default. 19 is a process that is less nice, right? So it's going to have higher priority on the system. And so in this case, if I expand this out, you'll see that the less nice process is journal D, which is logging daemon, which makes sense. Like I want to make sure my logging daemon is always doing its thing, even in the face of user workload. And we also have some RT or real-time processes running in this particular system. So the point about talking about things like task set and niceness are those are knobs that you get to turn to control workload. So if someone's being a little bit not nice to your system, you can use these tools to kind of push them into a corner. Docker has a fantastic interface to do that with limiting CPU utilization for a running container, which it's a great thing to do some testing with. All right. Any questions or comments around CPU, team? All right. So clock rate, big deal, huge deal, right? You saw the range of frequency. The ability to control P states and C states for high performance, big deal. And then you have some toys and tools to play with to control the actual workload running on the system. Sir?
When it went 100% in green, you're saying it's running in user mode.
Yes.
So when it goes, say you do an I/O, it goes into the kernel of the OS,
You know,
and then it goes off. How's that reported in HLOC? It goes red.
yeah. The question is, how is kernel mode reported in HTOP? That's called demo number 2, Andrew. You're getting, yeah, that's exactly where I want to see, right? Take you on the journey. So when we're looking at memory tuning, we talked about in the presentation, it's important that we have to have enough workload. We want to prevent swapping, but there's 2 different kinds of paging or swapping. There's anonymous paging, which is the bad stuff. That's the stuff we experience when I run out of memory. There's file system paging of memory mapped files, which is good paging, meaning I'm caching file I/O inside of memory. Now we're going to talk about who's more important in that context, right? And that's where swappiness is going to come in. So what I'm going to do now is I have a SQL Server running. I'm going to read in a 5 gig table. It's going to conduct I/O, Andrew. And it's going to be reported as kernel mode. So there we see tons and tons and tons of kernel mode I/O. I'm reading a 5 gig table off of disk and sticking it in memory. It's not just I/O that's kernel mode here. So yeah, I'm dispatching I/O to get the pages associated with that database off of disk. But I'm also allocating those page structures in memory too. So that's also a kernel call because I have to ask the operating system, say, hey, give me some memory for this thing, and then allocate that page. And so what we see now is I have 5 gigs of memory allocated to this particular workload. And we can see it here also. This is called resident set size, so about just over 5 gigs associated with the SQL Server. So you notice now all the red's gone away, and I'm just grinding on green now. There's a little bit of red, but not like the Christmas tree it was a few minutes ago or a few seconds ago. I have a hard loop reading that 5 gigs over and over and over again. So now I'm just accessing that in memory. When you access memory, it actually costs CPU, right? Because I'm reading pages from memory. And these are 8K allocated pages, 4K allocated pages from the operating system, right? So I'm ripping across billions of, or potentially millions of pages inside of the kernel space. When I say pages, the kernel structure representing the memory that's physically resident in the system. So that query finished, and it took about a minute. All right. So let's dive into where that stuff lives. So more proc meminfo /proc gives me a text interface into runtime statistics about the kernel, right? The current state of the platform. Okay. 12 gigs in the system. This is the file system cache. So not a lot of stuff read into the file system cache because SQL Server manages its own memory space, right? So there we see active anonymous pages about just over half a gig, or 5 gigs, excuse me. And if we go down a little bit further, I want to look at another metric. Yeah, anonymous pages reported here as well. And non-huge pages right now is about 83 megs. The kernel by default has the ability to allocate various page sizes. Again, the memory structure inside the kernel. And so it's allocating 4K pages at this point in time to my user workload. Cool. All right, let's go ahead and do a couple of things. I'm going to ask the kernel what its current configuration is for a thing called transparent huge pages. Transparent huge pages gives me an interface to ask the kernel for a giant page, right? And so by default, it's going to be 2 megs. It's of various size, but that actually represents 500 4K pages, right? So one page now represents what previously was 500 4K pages from the operating system. And so let's go ahead and switch it from madvise to enabled. And we can do that with this code here. And check that setting there. Okay, so I changed that at runtime. Right, this is a way for me to interact with the kernel directly via this interface. So guess where I'm going to actually persist it, though? In ToonD when we're done. Okay? So let's do this now. I'm going to turn on a particular trace flag inside of SQL Server that tells SQL Server to also think in large pages. Okay? So 834 allocates 2 meg pages inside of SQL Server as well. So I'm going to bump that SQL Server service. But you're going to notice something different happens this time right here in the memory allocation. When that restarts, it's going to hopefully start allocating pre-allocating the memory. So what's happening when SQL Server starts, it's going to allocate or pre-allocate the max memory size, or the 8 gigs. And so at this point in time, I'm paying the penalty for all the page allocation access that I did a second ago in the previous workload, right? And so once that's up and fully populated, all that red's going to go away. And that's all the kernel mode allocations of the memory structures, which happened last time when I ran that against the cold buffer pool. So here you can see I am using large pages in the memory manager. That's the important part there, to make sure that that configuration is actually affected. And so now when I run the same exact query, we're going to get a little bit of red, but a lot less red than it was last time. Remember last time the entire graph was almost entirely kernel mode because IO and memory allocation, so the workload wasn't running great. And remember the runtime of this query in the previous one was about a minute, I think it was. Yeah, it was 1 minute and 1.2 seconds. And when this finishes, it should be around 40 seconds. So any questions or comments while we awkwardly wait for the next 40 seconds?
Which time zone is that in? Can you guess who asked that question?
This is,
Also repeat the question.
the question is, what time zone is it? It's in this time zone, I guess? No, we're +1 right now, right?
And the second question was, can you guess who asked that question? Correct.
But notice we're, by just pre-allocating the memory 15 seconds faster. That's a non-trivial increase in performance for a particular workload, right? Now there's some nuances to 834 when it comes to actually running that on production systems. But what I want to highlight here is how an application interacts with memory, right? Our ability to control that and the impact of that on a workload, okay? Now if I go and I ask for /proc/meminfo again, let's see, active anonymous 8 gigs, because that's the entire working set for SQL Server, even though the table that we read was 5 gigs. And if I go down to the bottom here, we could see the majority of that is in anonymous huge pages, or 2 meg pages. Cool?
Nancy,
Yes.
what's the difference between active and non?
Active and non. I'm processing the question so that I can answer it. Well, what the question is, what's the difference between active and non? These pages are allocated by a user process. These pages are just allocated, period. Okay. All right, so other parts of the operating system that are allocated. Good question. Yeah, memory accounting is a tough one. I think, did I include it in here? I did. So if you click on this link here in the charts, it's going to have, I should have called this out specifically, all of the different ones and how they're calculated. Some of them are calculations of others. Yeah. And so this gets super nerdy super fast. Good question, Andrew. Cool. Yeah, there's tons of links sprinkled throughout. I should be calling them out as I go through, but I get too excited by this nerd stuff. All right. So we know now that we have 12 gigs in our system. I've allocated 8 gigs to SQL Server to do some stuff, and I have about 1.5 gigs free, right? This is the file system cache. So any file IO that's transacted while the system's been up, the pages associated that were read from the file system are actually in memory right now. So if I go hit that file again, I'm actually not going to hit that file again. I'm going to get it from memory, right? Sounds great, huh? Faster, right? Nanoseconds versus milliseconds, unless you're on our platforms, but that's another show. So I'm going to read a giant 1.6 gigabyte file, which I built on the airplane by just hitting Control-C and Control-V a whole bunch. So you can see here a bunch of file IO, lots of red, right, is occurring right now. But that's not what I'm going to highlight with this demo. All right, once that's finished, I'm going to ask the operating system again, how much do you have in cache? So I went from 2 gigs to 3.4 gigs, right? Because that entire file is now cached in memory. If I hit it again, ideally I should see no IO, right? There should be nothing there. Of course it is. I have no idea why it's doing that, but it was a heck of a lot faster. Okay, cool. Now I'm going to make my computer system extremely sad, like very, very sad. So I wrote this program called memtest. What it's going to do is it's going to create a process that's going to allocate 6 gigs of memory, which I don't have 6 gigs of memory left, right? I have just about 3 gigs. Right, but I chose 6 gigs intentionally because if I do anything more, it's going to do a whole another thing, which we'll talk about in a second. So let's go ahead and run that. And what we see here is a whole bunch of sadness is occurring. So that's me allocating the 6 gigs. So if I look in this list here, we should see my program filtering to the top. Maybe if I sort by resident set size. Of course, all the SQL Server stuff is there. Where's mine? Yeah, right there. So 6 gigs, lots of red. And now swapping's occurring. So I'm filling up the swap. So guess what's going into the swap right now? Big swaths of memory. About 3 gigs is now written into the swap file. And so my program runs in a hard loop. And so I'm touching all of that memory constantly, keeping it hot, preventing it from being swapped out. The buffer pool from SQL Server, some of that got swapped out. Some of it will actually get deallocated. So you have to make sure that your applications respond correctly to high memory situations. So I'm completely out of memory. I'm not crashing. I'm on the verge of crashing. If I allocated another gig, what would start happening is the operating system would kick in a thing called the OOM killer, or the out of memory killer, and start arbitrarily killing processes. It's like the chaos monkey inside of our platform here. So let's do this. Let's kill that thing to make the system less sad. And let's look at the memory topology again. So my entire file system cache was completely evacuated. That swappiness setting that we talked about in the beginning, right? That's a parameter that I can tune to basically say, how fast am I going to dump that cache, right? So this is a database engine that manages its own cache. So I want that cache to dump as fast as possible because I want all of that to support the database engine. But if this is a web server or a file server, I might not want to do that because I want that file system cache to support the responsiveness of my workload, right? And so that value is dependent upon that. So right now the value is 10 for swappiness. It tips it over and it gives as much of that as it can to the other user processes that are actually in memory. So that's what happens to your file system cache under high memory situations. So yeah, it's this CTL. You can see right now it's 30 actually, not 10. Defaults to 10, but when we set our ToonD profile, it will be 10. Cool. So let's do some stuff with ToonD. We have a SQL Server profile, which sets a maxed memory mapped file count in terms of size and our throughput performance. So a lot of the values that we've been walking through should be in here now. So here we can see CPU. I had to omit a demo. I am so sorry, team, because this would be another 2 hours if I kept going. But I do have a whole bunch of demos on read ahead at the bottom. Read ahead involves a whole nother set of commands that I have to go and configure. But for this particular ToonD profile, we're going to set a 4K read ahead at the file system level. Let's see, going forward. So, yeah. We have some other things with regards to this kernel scheduler. What we see here is 2 parameters that have to do with how fast an asynchronous thread is awoken when its IO is complete. And so this is some fine tuning on systems that do lots of disk transactions like a SQL Server, right? Cool. And what else do we have in here to work with? The dirty ratio with regards to how much of a process address space is changed. PIDMax is commented out, but that's the maximum number of process IDs, and we're going to choke down or lower swappiness to 10, how fast it tips over that cache. And so those are our 2 settings. And so to enable all of that goodness, now I just do this. So rather than typing block dev and going to sysctl or adjusting in the procfs, I can just affect this change by doing that. And so if I ask sysctl now 10, and I didn't have to go write that in a file and do all of those things. Cool. Let's go ahead and see who is active. Bing. Yeah, so MSSQL is active. Cool. All right, any questions or comments, team? Good. Do you want to keep going? Or do you want to stop since it's technically only a 30-minute presentation? All right. Keeping y'all from the beer. All right, so additional demos. When you interact with a file, every file has metadata associated with the file, right? Meaning the operating system is doing some accounting on what exists. And so I can ask the operating system for the file metadata about a particular file. And so I'm saying sudo stat on this transaction log file. Every time I access a file, just access it for read, not write, well, also write, create, change. But every time I access it, it's going to update that metadata. Now think about that from a high transaction throughput system, right? It's going to update that metadata all the time. And so what we can do is we can adjust the file system mount to no longer update that A time. Now, is this a good thing? I don't know, because you have to deal with the fact that you might be needing that from a security standpoint for some things. However, what I did for this particular system, I peeled off what I wanted to have no A time, or excuse me, I peeled off I dedicated a particular file system and drive for this setting. So the rest of the operating system still has this configured. I have some nerd gymnastics here if you want to do these on your own. And I would encourage you to do that with regards to see this in action. But I'm going to jump over that because I want to show you how to make this change. I could offline the database, but right now what I'm going to do is I'm going to stop the SQL Server and I'm going to go into FS tab. In FS tab, I have pre-configured the settings that I want. And so here we can see my data volume in /data is an XFS file system, all the default parameters, but add no A time. And so if you were in Andrew's session about running PowerShell in Vim, you would be seeing a different user experience right now. All right, so I commented out this one and I added this one, saved that out. I have to reread the file because I am running systemctl or systemd, excuse me. Remount, sudo remount, sudo make me a sandwich. Run that there and start my SQL Server. And so now if I go and I do I'll do this just to be explicit for the video, copy and paste that down. This A time will stop getting updated as that changes. So we can see the access time has stayed behind, but the modifier is moving forward in time. Cool. All right, let's look at read ahead. I'm surprised I was able to get to all these because when I did this in the hotel room all week, I did not get to these demos in 30 minutes. So that is no A time. I mean, now that access won't be updated every time I touch the transaction log file or any file in that file system, and even on the database files. But the one that we would consider most is the transaction log file from a database performance standpoint. So sudo block dev. All right, so right now read ahead is set at 256, but I want it to be 4K. And so I can do that by using the block dev command, set RA on that particular disk. I'm gonna run that here. And now we can see read ahead is set to 4K. Funny enough, that should have been set by ToonD. So I have to go figure out why that didn't stick when we set that earlier. And so let's take that into account when we do this again. Cool. So now I have that enabled. So as I start reading disk, if I start scanning, I'm going to read the next 4K every time, right? And so that'll be in memory and reduce the amount of IO that I have to do. Cool. So going back up here, I do have settings to put the system back into the original state. So we're going to go back to our virtual profile. I'm going to turn off 834, bump my SQL Server instance. And since our memory accounting is complete trash because of all the nasty things that I did to the system, I'm going to reboot the box. And the idea here is if you want to do these demos on your own, this is how you restart to get back to like a clean system. And you kind of march through all of the badness that we did to the operating system while we went through all of that. What is that back there? Oh, yeah, I'm rebooting. Cool. There was a couple things to call out. If you do want to repeat these demos, the 12 gig number was chosen intentionally for SQL Server because to use that trace flag 834 for the large memory allocations, you need at least 8 gigs of memory in the system. So that was chosen intentionally. So if you try to reproduce this, you're going to need that. So here, we have a few minutes left. Let's open up for questions, team.
Do you think, maybe you don't know the answer, but for the Windows part, we can have the same granularity of those settings like we have in Windows?
So the question is, do we have the same like feature parity, I guess, or settings parity in Windows? I would imagine yes, but I have no idea because I don't go to that level of detail in performance tuning on Windows. I know all the power plan stuff exists. On the memory side, I don't know if we have an interface to control things like swappiness, but you do have control over things like where your swap files live and how big and small they are, things like that. Let's see, what else would you have to mess with?
I know.
You know what? I'll look into that. I haven't gone to that level of granular and perform.
Also, but the Postman, for that we know, the swap file also, but maybe there is some settings that you have to
Yeah.
in the registry.
I would imagine, yeah, that would definitely be where they'd be exposed. That or particular commands. Right. Cool. Good question. All right. You ready?
Where they are exposed for the records.
What's that?
Where they are exposed.
I don't.
The registry.
Oh, they are?
Just for the records.
Yeah. Oh, the statement is settings like this would be exposed in the Windows registry. Yes. Cool.
This is a dozy question. Though. Why was the read ahead set to 4 KB and not 8 KB?
I'm trying to think of the answer too. All right. My brain is asynchronous as I get older. Okay. Or synchronous, I guess you could say. The question is why 4K for the read ahead and not 8K? If you think about that particular file system is XFS, and the file system allocation unit or block size is 4K for this particular system. And the recommendation from Microsoft for SQL Server specifically is 4K.
So it's the file size allocation unit, not the data page within the file.
Correct. But because we also manipulated the size of the page too in memory, the in-memory page, right, to 2 megs.
Can you repeat his correct statement?
What was the statement?
It's the file allocation unit size, not the size of the page within the SQL Server file.
Correct. Yeah. And yeah, that's what I said. It has to do with the XFS is 4K block. So the statement is, what is it?
The file allocation.
It's the file. But it's in it's not. It's. Oh, really? That's how we're going to do this. Read ahead has to match block size for this particular recommendation from Microsoft. Again, your mileage may vary on your application and your workload. Cool. You owe me a beer now. All right. Thanks, team.